And now in this lecture we'll answer two questions. In the first question we'll find out the area of this green triangle, triangle ABC. And in the second question we'll find out the length of this line segment AP. This is equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have quadrilateral PQABCP, and we know that AQ equals to AC. This is angle QPC, that is equals to 60 degrees inside. This is angle ABC, that is also equals to 60 degrees inside. This is line segment AB, that is equals to 5 units in its length. This is line segment CP, that is equals to 4 units. Line segment CP equals to 4 units in its length. And this is again PQC, that is the right angle. Again, our task is to find out the area of this green triangle, triangle ABC. So first of all, we will do a construction. That is from this point A, we will do perpendicular on QP. Again, from point A, we will do perpendicular on the base QC. Actually, triangle AQC is an associated triangle because side AQ equals to side AC, and QC is the base of the associated triangle, triangle AQC. So from the vertex A, we will do perpendicular on the base QC. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and QC. This point is point M. We have the rule that says that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So according to the rule that I mentioned, the perpendicular AM to the base QC bisect the base QC. That is to say, the perpendicular AM divides the base QC into two halves. The first half is QM and the second half is MC. And of course that the first half must be equal to the second half. So QM equals to MC. So if we define the length of QM as A, then the length of the second half MC must be also equal to A. In the next step, we will extend the perpendicular AM by straight line until it touches side PC. We define the touching point of the extended perpendicular AM with side PC. This point is point N. In the next step, we will focus on the right big triangle, triangle PQC. The right big triangle PQC, 90 degrees plus 60 degrees is 150 degrees. And therefore this third missing angle must be equal to 30 degrees in its size, according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. AM as a perpendicular, it is absolutely a straight line. When you extend a straight line by straight line, the result AN must be also a straight line. So AN is a straight line. If you focus on the right side of the straight line AN, if we focus on the right side of the straight line AN, it's point M. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN, it's point M. We have this angle that is the right angle plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the small right triangle, NMC, 90 degrees plus 30 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in size, according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. Therefore this third missing angle must be equal to 60 degrees in its size. Actually, it is very easy to see that the big right triangle PQC is similar to the small right triangle NMC. I'll prove it anyway. Why the big right triangle PQC is similar to the small right triangle NMC? First of all, this is angle C, that is equal to 30 degrees in its size. Angle C is a common angle that belongs to both triangles. Angle C belongs to the big right triangle PQC. Angle C also belongs to the small right triangle NMC. So we can write out that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So we should find out that all the figures of the big right triangle PQC are correspondingly equal to all the figures of the small right triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. I should find out that the big right triangle PQC is similar, this is the sum of similar to the right small triangle NMC. According to angle similarity rule. And from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle QPC. So repeat again, from the fact that the big right triangle PQC is similar to the small right triangle NMC, we derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is. Over PC. PC equals to 4 units in its length, according to what is given as the question. And it is equal to MC. MC equals to A units in its length, according to our definition. Over QC. QC in total equals to A plus A, that is 2A. So in total, we actually found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. After we cancel A, in this side of the equation we left only with 1/2, so 1/2 equals to NC over 4. Here we will multiply this equation by 4 and finally get the missing side NC. Is equal to 4 over 2, that is 2. NC equals to 2 units in its length. This is the missing side NC, that is equals to 2 units in its length. In the next step, I'll copy the big triangle A and B in a new pageant, we will analyze this big triangle, triangle A and B. Side AB of the big triangle A and B equals to 5 units in its length according to what is given as the question. This is angle ABC, that is equals to 60 degrees in size. Also according to what is given as the question, and we already found out that this is angle A and B, that is equals to 60 degrees in its size. So actually, this is the big triangle A and B that are going from the original drawing. In this big triangle A and B, 60 degrees plus 60 degrees is 120 degrees. And therefore, this third vicinity must be equal to 60 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So if you found out that the big triangle A and B is an equilateral triangle. So I write it down. The big triangle A and B is an equilateral triangle. And we know that all the sides of an equilateral triangle are equal to each other. AB equals to 5, therefore AN must be also equal to 5 units in its length, and B must be also equal to 5 units in its length. What is the length of the missing 97 CB? CB equals to NB minus NC. Again, CB equals to NB minus NC. So I write it down. CB equals to NB minus NC. So CB in total equals to NB. NB is one side of the equilateral triangle NB that is equals to 5 units. Minus NC. NC equals to 2. So in total CB equals to 5 minus 2, that is 3. So she found out that CB equals to 3 units in its length. CB equals to 3 units. In the next step, we will do another construction, that is to say from point A, we will do perpendicular on CB. Again, from point A, we will do perpendicular on CB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in CB. This point is point O. By doing this construction, we can do the right hand triangle, triangle AOB. We define side AO as H, that is to say AO equals to H units in its length according to our definition. In the next step, I'll copy the right hand triangle, triangle AOB in a new page, and we will find out the length of AO that is equals to H. The hypotenuse AB of the right triangle AOB is equal to 5 units in its length according to what is given as the question. So actually, this is the right triangle AOB that are coming from the original drawing. In this right triangle AOB, this angle equals to 60 degrees and inside according to what is given in the question. So this right triangle AOB, sinus 60 degrees is equal to AO over AB. AO equals to H, AB equals to 5. So the total actually found out that sinus 60 degrees equals to H over 5. Sinus 60 degrees is equal to square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here we will multiply this equation by 5 and finally get that H equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So what is the area of the green triangle, triangle ABC? The area of the green triangle ABC must be equal to the base CB times the height H over 2. So again, the area of this green triangle, triangle ABC must be equal to the base CB times the height H over 2. CB equals to 3 units in its length. We just went on that H equals to 5 times root of 3 over 2 units in its length, and we have to divide it by 2. So today we actually found out that the area of triangle ABC is equal to 3 times 5 is 15, so in total in the numerator of this expression we have 15 times root of 3 divided by 2 times 2, that is 4. So in total we actually found out that the area of this green triangle, triangle ABC is equal to either 15 times root of 3 over 4 square units in its size, or in terms of numbers, the value of this expression is equal to 6.5 square units in its size. So if it again, I actually found out that the area that we're looking for in this question, that is the area of this green triangle ABC, is equal to either 15 times root of 3 over 4 square units in its size. In terms of numbers, the area of this green triangle, triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will answer the second question of this lecture. In the second question, our task is to find out the length of this small short line segment AP that is equals to x. We have to find out the value of x. So in the drawing, we have a semicircle. Point O is the center of this semicircle. Line segment PO equals to 10 units in its length. This is line segment QP that is equals to 21 units in its length. This is called QS that is equal to 16 units in its length. This is angle PQS that is equals to 90 degrees in its size. Again, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So first of all, we will complete this semicircle to a circle. So we completed the semicircle to a circle, and we will extend line segment QP by sideline until it touches the circle. We define the touching point of the extended line segment QP with this circle. This point is point M. The next step, we join points S and M together by straight line. So, by doing all those constructions, we get the deal. Peripheral SQM, peripheral SQM equals to 90 degrees in size, and peripheral SQM subtend on code SM. Again, peripheral SQM subtend on code SM. Here we can implement Rule 5. So, I'll repeat click on Rule 5. According to Rule 5, any peripheral that is equals to 90 degrees must subtend on the diameter of the circle. In the normally we have a circle. This is peripheral MAB that is equals to 90 degrees in size, and therefore peripheral MAN must subtend on the diameter of this circle, and indeed peripheral MAN subtend on MN, that is the diameter of this circle. So according to Rule 5, any peripheral that is equals to 90 degrees in size must subtend on the diameter of the circle. In our drawing, we have peripheral MQS that is equals to 90 degrees in size, and therefore it must subtend on the diameter of this circle. Peripheral MQN subtend on SM, and therefore according to Rule 5, SM must be the diameter of this circle. So I'll write it down. Chord SM must be the diameter of this circle according to Rule 5. If SM is the diameter of the circle, we have a point O in the center of the circle, point S is the point on the circle itself, therefore OS is the radius of this circle. We define the radius of this circle as R, therefore OS equals to R, it is the radius of this circle. Likewise, OM is also the radius of this circle, therefore it is equal to R units in its length. In the next step, we will do a construction, that is to say, from point O, that is the center of this circle, we will do perpendicular on QP. Again, from point O, we will do perpendicular on QP. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. The next step we will focus on this angle M. This is angle M, that is a common angle that belongs to both triangles. Angle M belongs to the big right triangle, triangle SQM, and angle M also belongs to the small right triangle, triangle ONM. So we define the size of this angle M as alpha, and we will focus on the right big triangle, triangle SQM. On the right big triangle SQM, this angle equals to alpha, this angle is the right angle, this is equals to 90 degrees in size. Therefore, this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the small right triangle O and M, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Actually, it is very easy to see that the big right triangle SQM is similar to the small right triangle, triangle O and M. I will prove it anyway. So, why the big right triangle SQM is similar to the small right triangle, triangle O and M? First of all, this is angle M, that is a common angle that belongs to both triangles. So we can write down that angle M equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the angles of the big right triangle SQM are correspondingly equal to all the angles of the small right triangle, triangle O and M. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle, triangle SQM is similar, this is the sign of similar, to the small right triangle, triangle O and M, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side NO of the small right triangle, triangle NOM, over side QS of the big right triangle, triangle SQM, is equal to side OM of the small right triangle, triangle NOM, over side SM of the big right triangle, triangle QSM. So repeat again, from the fact that the big right triangle SQM is similar to the small right triangle, triangle O and M, we derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle O and M over side QS of the big right triangle SQM is equal to side OM of the small right triangle O and M over side SM of the big right triangle, triangle SQM. ON is the missing side, so we leave it as it is, over QS. QS equals to 16 units in its length according to what is given as the question. And it is equal to OM, that is R, it is the radius of this circle, over SM. SM is the diameter of this circle according to rule 5, therefore it is equal to 2R. So in total, we actually found out that ON over 16 equals to R over 2R. So here we have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation we left only with 1/2. 1/2 equals to ON over 16. Here we will multiply this equation by 16 and finally get that ON equals to 16 over 2, that is 8. So we found out that the length of the missing side ON is equal to 8 units. This is the missing side ON. This equals to 8 units in its length. In the next step, we will do another construction here. What is we implement the Pythagoras theorem on this small right triangle P and O. But what is the length of actually we know that the diameter of this small right triangle, this is the small green right triangle P and O. The diameter PO equals to 10, side ON equals to 8, and NP is the only missing side that we have here. So we copy the green small right triangle P and O in the new page, and we will implement on it the Pythagoras theorem. Here by PT is the version for Pythagoras theorem. The hypotenuse PO equals to 10 units in its length. Side PN is the missing side. And O equals to 10 units in its length according to what we have already found out. So actually, this is the right green small triangle P and O that I copied from the original drawing. This right small triangle P and O, PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. The hypotenuse PO equals to 10 units in its length, therefore PO squared is 10 squared, that is 100. And it is equals to Pn squared. Pn is the missing side, so we leave it as it is. Pn squared plus NO squared. NO equals to 8, therefore NO squared is 8 squared, that is 64. So in total we found out that 100 equals to Pn squared plus 64. Here we will subtract 64 for this equation and find that 100 minus 64 is 36. So Pn squared equals to 36. Here we will take a root out of this equation and find that the missing side Pn is equal to the square root of 36, that is 6. So if you found out that the length of this missing side Pn is equal to 6 units. What is the length of the missing 97 QN? From the drawing it is very easy to see that Qn in total equals to QP minus NP. Again, Qn equals to QP minus NP. So I write it down. Qn equals to QP minus NP. So Qn in total equals to QP. QP equals to 21 units in its length, according to what is given as the question. Minus NP. NP equals to 6 units, according to what we have already found out. So in total, Qn equals to 21 minus 6, that is 15. So we have found out that the missing 97 Qn is equal to 15 units in its length. This is the missing 97 Qn. That is equal to 15 units in its length. In the next step, I will join points Q and O together by straight line. Point O is the center of this circle, point Q is the point on the circle itself, therefore OQ is the radius of this circle, that is equals to R according to our definition. In the next step, I'll copy the right triangle Q and O in a new page, and we will implement the Pythagoras theorem on this right triangle Q and O. Here by PT is the measure for Pythagoras theorem. So actually this is the right triangle Q and O that I copied from the original drawing. This right triangle Q and O, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, is equal to QN squared plus NO squared. Okay, again, in this right triangle Q and O, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. The hypotenuse QO equals to R, therefore QO squared is R squared, and it is equals to QN squared. QN is 15, therefore QN squared is 15 squared, that is 225, plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total we actually found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So if you found out that R squared equals to 289, here we will take a root out of this equation and find again that R, the radius of the circle, is equal to the square root of 289, that is 17. So if you found out that the radius R of this circle is equal to 17 units in its length. OA is also the radius of this circle, that is equals to R. The radius of this circle is also OA, is equals to R, and R equals to 17. But OA also equals to AP plus PO. Again, OA in total equals to AP plus PO. So I write it down. OA equals to AP plus PO. AP is the line segment that we are looking for in this question. AP equals to X plus PO. PO equals to 10 units in its length according to what is given in the question. And from this long equation, we derive that X plus 10 equals to 17. Again, X plus 10 equals to 17. X plus 10 equals to 17. Here we subtract 10 from this equation and find again that X equals to 7 minus 10 is, again, X equals to 17 minus 10, that is 7. X is the length of line segment AP. AP equals to X. So we actually found out that the length of line segment AP is equals to X is equal to 7 units. Okay, again, we actually found out that the answer to this question is the length of this short line segment AP that is equals to X is equal to 7 units. So we finish with the second question. The next step, I will summarize the lecture. We start with the first question, of course. The first question, our task is to find out the area of this green triangle, triangle ABC. So in the drawing, we have coordinate QABCP. We know that AQ equals to AC. We know that AB equals to 5 units in its length. This is line segment PC, that is equals to 4 units in its length. This is angle QPC, that is equals to 16 degrees in its side. This is angle ABC, that is also equals to 16 degrees in its size. And this is angle PQC, that is equals to 90 degrees in its size. Again, our task is to find out the area of this green triangle, triangle ABC. In the first step, we did a construction, that is to say from point A, we do perpendicular on QC. Again, from point A, we do perpendicular on QC. So clearly this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in QC. This point is point M. This is triangle QAC, that is an associated triangle because side AQ equals to side AC according to what is given in the question. QC is of course the base of this associated triangle, triangle QAC. So from the vertex A we do perpendicular to the base QC. Again, from the vertex A we do perpendicular on the base QC. And we have the rule that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. That is to say, the perpendicular AM to the base QC bisect the base QC. That is to say, it divides the base QC into two halves. The first half is QM and the second half is MC. And of course, QM equals to MC. So if we define the length of QM as 8, then the length of MC must be also equal to 8 because they are equal to each other. In the next step, we extended the perpendicular AM by side line until it touches side PC. We define the touching point of the extended perpendicular AM with side PC. This point is point N. AM is a perpendicular, it is absolutely a straight line. We extended the straight line AM, we extended the straight line AM by straight line, and we will extend a straight line by straight line, the result must be a straight line. Therefore, the result AN must be a straight line. So if we focus on the right side of the straight line AN, it's point M. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AM at point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the right big triangle, triangle PQC, 90 degrees plus 60 degrees is 150 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle, triangle MNC, 30 degrees plus 90 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in its size according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the big right triangle QPC is similar to the small right triangle, triangle MNC. I will explain anyway why the big right triangle QPC is similar to the small right triangle, triangle MNC. First of all, this is angle C, that is equals to 30 degrees in its size. Angle C is a common angle that belongs to both triangles. So you can write down that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the figures of the right big triangle PQC are corresponding equal to all the figures of the small right triangle, triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So if you found out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle, triangle NMC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle QPC is equal to side MC of the small right triangle NMC over side QC of the big right triangle QPC. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is. PC equals to 4 units in its length according to what is given as the question, and it is equals to MC. MC equals to A units in its length according to our definition, over QC. QC equals in total to A plus A, that is 2A. So if you found out that NC over 4 equals to A over 2A. Here we have A in the numerator and A in the denominator, so A will get cancelled. After we cancelled A, we left here with 1/2. 1/2 equals to NC over 4. Here we multiply this equation by 4 and finally found out that the missing side NC equals to 4 over 2, that is 2. So actually this is the missing side NC, that is equals to 2 units in its length. In the next step, I copy the big triangle A and B in a new page and analyze this big triangle A and B. This is the big triangle A and B that I copied from the original drawing. Side AB equals to 5 units in its length according to what is given as the question. This is angle ABN, that is equals to 60 degrees in its size according to what is given in the question also. This is angle A and B. We already found out that angle A and B equals to 60 degrees in its size. So 60 degrees plus 60 degrees is 120 degrees. 120 degrees, so this third triangle must be equal to 60 degrees in its size according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the big triangle A and B, all the triangles are equal to each other, each of them is equal to 60 degrees, and therefore this triangle A and B must be an equilateral triangle. And we know that all the sides of any equilateral triangle are equal to each other. AB equals to 5, and therefore AN must be also equal to 5, and NB must be also equal to 5 units in its length. What is the length of the missing side CB? From the drawing it is very easy to see that CB equals to NB minus NC. Again, CB equals to NB minus NC. So CB equals to NB, that is equals to 5. It is one side of the equilateral triangle A and B. Therefore it is equals to 5 units in its length. Minus NC. NC equals to 2. So in total CB equals to 5 minus 2, that is 3. CB equals to 3 units in its length. In the next step, we did another construction, that is to say from point A, we do perpendicular on CB. Again, from point A, we do perpendicular on CB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. In the next step, I call it the right hand triangle AOB. In the new page, analyze this triangle AOB. We define the length of side AO as H. So I call it the right triangle AOB. In a new page, we found out the length of the missing side AO that is equals to H. So actually, this is the right triangle AOB that I call it from the original drawing. AO equals to H according to our definition. AB equals to 5 units in its length according to what is given as the question. So in this right triangle AOB, sinus 60 degrees equals to AO over AB. Again, sinus 60 degrees equals to AO over AB. AO is H, AB is 5, so in total sinus 60 degrees equals to H over 5. Sinus 60 degrees equals to H over 5. Sinus 60 degrees is square root of 3 over 2, so square root of 3 over 2 equals to H over 5. Here we multiply this equation by 5 and finally found out that H equals to 5 times square root of 3 over 2 units in its length. So H equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So what is the area of this green triangle, triangle ABC? The area of this green triangle ABC must be equal to the base CB times the height edge over 2. Okay, again, the area of this green triangle ABC must be equal to the base CB times the height edge over 2. CB is 3, edge is 5 times square root of 3. Again, CB is 3 and edge is 5 times square root of 3 over 2 divided by 2. We have to divide it by 2 again. So here we have total the area of the green triangle ABC is equals to 3 times 5 is 15. So in total, in the numerator of this expression, we have 15 times square root of 3 over 2 times 2, that is 4. So actually found out that the area of this green triangle, triangle ABC is equal to either 15 times square root of 3 over 4 square units in its size. So in terms of numbers, the area of this green triangle, triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. The next step, I presented to you the second question, and we answer the second question, also on the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP that is equal to x. We have to find out the value of x. So in the domain we have a semicircle. Point O is the center of this semicircle. Line segment PO equals to 10 units in its length. This is line segment QP that equals to 21 units in its length. This is called QS that is equals to 16 units in its length. And this is angle PQC that is equals to 90 degrees in its size. Again, our test is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So first of all, we completed this semicircle to a circle, and we extended line segment QP by a straight line until it touches the circle at this point. We define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we join points M and S together by a straight line. By doing all those constructions, we can then do peripheral angle SQM. Peripheral angle SQM equals to 90 degrees in its size. And according to rule 5, any peripheral angle that is equals to 90 degrees in its size must subset on the diameter of the circle. Peripheral angle SQM is equals to 90 degrees in its size, and its subset on chord SM. And therefore, according to rule 5, chord SM must be the diameter of this circle. SM is the diameter of the circle according to rule 5. Point O is the center of the circle. Point S is the point of the circle itself. Therefore, OS is the radius of this circle. We define the radius of this circle as R. So OS equals to R. Likewise, OM is also the radius of this circle. That is equal to R according to our definition. In the next step, we did the construction. This is to say, from point O, we do perpendicular on QP. Again, from point O, we do perpendicular on QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. So by doing this construction, we can then do the small right triangle, triangle O and M, and we have also the big right triangle, triangle SQM. This is angle M that is a common angle that belongs to both triangles. Angle M belongs to the small right triangle O and M, and angle M also belongs to the big right triangle, triangle SQM. We define the common angle M as alpha. So in the big right triangle SQM, alpha plus 90 degrees plus this missing angle, in total they must be equal to 180 degrees according to the rule that the sum of the angles in the triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the small right triangle O and M, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. It is very easy to see that the big right triangle SQM is similar to the right small triangle, triangle ONM. I will prove it anyway. First of all, this is angle M, that is a common angle that belongs to both triangles, so we can write down that angle M equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can find out that all the angles of the right big triangle SQM are correspondingly equal to all the angles of the small right triangle, triangle ONM. And therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again, if we find out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle, triangle ONM according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle, triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side QS of the big right triangle, triangle SQM is equal to side MO of the small right triangle, triangle ONM over side SM of the big right triangle, triangle SQM. I repeat again, from the fact that the big right triangle SQM is similar to the small right triangle, triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle, triangle SQM. ON is the missing side, so we leave it as it is over SQ. SQ equals to 16 units in its length according to what is given as the question. And it is equals to OM. OM is the radius of this circle, that is equals to R over SM. SM is the diameter of this circle, and therefore it is equal to 2R. So in total we found out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. So we left here only with 1/2 equals to ON over 16. Here we multiply this equation by 16 and find out that the missing side ON equals to 16 over 2, that is 8. So actually this is the missing side ON, that is equals to 8 units in its length. In the next step I copied the right grain small triangle ONP in a new page and we implemented the Pythagoras theorem on this right small grain triangle, triangle ONP. This is the right grain small triangle ONP that I called from the original domain. In this right triangle ONP, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to NP squared plus NO squared. OP is 10, therefore OP squared is 10 squared, that is 100, and it is equals to NP squared. NP is the missing side, so we leave it as it is, so it is NP squared plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total we actually found out that 100 equals to Pn squared plus 64. Here we subtracted 64 from this equation and finally found out that 100 minus 64 is 36, so 36 equals to Pn squared. Here we took out of this equation and finally found out that the missing side Pn equals to the square root of 36, that is 6. This is the missing side Pn, that is equals to 6 units in its length. What is the length of the missing 9797 Qn? From the dominant it is very easy to see that Qn in total equals to Qp minus Np. Again, Qn equals to Qp minus Np. And again, Qn equals to Qp minus Np. So Qn equals to Qp, that is 21 according to what is given as the equation, minus Np. Np equals to 6. So in total, Qn equals to 21 minus 6, that is 15. This is 97 Qn, that is equal to 15 units in its length. In the next step, we join points O and Q together by side line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle, that is equal to R. So in the next step, I commit the right triangle QON in a new page and we implemented the Pythagoras theorem on this right triangle QON. This is the right triangle QON that I copied from the original domain. QN equals to 15 units in its length, NO equals to 8 units in its length, and the hypotenuse QO is the radius of the circle that equals to R. In this right triangle QON, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. QO is R, therefore QO squared is R squared, and this is equals to Qn squared. Qn is 15, therefore Qn squared is 15 squared, that is 225, plus On squared. On is 8, therefore On squared is 8 squared, that is 64. So in total we found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So if we found out that in total R squared equals to 289, here we took out of this equation and found out that the radius R of the circle is equal to the square root of 289, that is 17. Okay, again, the radius R of this circle is equal to 17 units in its length. So OA is also the radius of this circle, that is equals to R, and R equals to 17. Okay, again, OA is also the radius of the circle, that is equals to R, and R itself equals to 17. But OA also equals to AP plus PO. So you can write here that OA equals to AP plus PO. AP is the line segment that we're looking for in this question, that is equals to X, and PO equals to 10. Repeat again, AP equals to X and PO equals to 10. From this long equation, we will derive that 17 equals to X plus 10, or X plus 10 equals to 17. Here we subtracted 10 from this equation and found out that X equals to 17 minus 10, that is 7. So AP, that is equal to X, is equal to 7 units in its length. So the answer to this question is the length of the short line segment AP, that is equal to X, is equal to 7 units. Okay, thank you very much.